I regret that English has become the dominant language, because there is one language which is much more beautiful to use for international scientific discussions, and that's Dutch. And this leaning tower here, that has been used by a Dutch scientist whose name is Simon Stevin. And he has been doing an experiment with having two lead balls falling down from the leaning tower and finding out that they fell on the floor at the same moment. That has been done with that tower by Simon Stevin. And he has also made sure that in the Dutch language, there are Dutch words exclusively for mathematics, for physics, and for lots of mathematical expressions. And they are exclusively Dutch, and we learn them at school. And then when you go across the border, you find out nobody else uses those words, and everybody speaks about mathematics or mathématique in French or in German. And so it is always painful to go across the border, but it's always enriching. I've started this picture for a variety of reasons. This leaning tower is still there, but also I wanted to point out to you that this is a painting of Vermeer, and that is a painting which is named Girl with a Pearl Earring. It doesn't have to do anything with physics, but what you can see is that you may have an iPad, or an iPod, or an iMac, or perhaps an iWatch. But you can see Vermeer was really very early. He was Vermeer, right? You see that? Very well ahead of his time. Well, the reality is, his first name was Isaac, so that is his name. But he has made also a picture of this person here. The picture is called Geographer, but it's a picture of Van Leeuwenhoek. That is the most famous scientist from the early days in Delft. I'll come to that in a minute. This is the current library in Delft. We have an architectural school, and they love to make fancy buildings. So this is our concept of a hill. In the Netherlands, that's flat. You have only polders, so all these meadows are flat. And then what you do is you take a roof and you grow grass on it. So we have now a hill, right? And this is then a cone, which is this cone here. And then you have here the bookstore, and this is sort of the outside of the building, just to give you some flavor of modern and old together. But I should speak about superconductivity at some point. Superconductivity is a branch of physics, but I'm an experimental physicist. Well, not really. My hands are no longer getting dirty because I interact with people who make their hands dirty, and that's a very fruitful combination. Well, if you go to Wikipedia, you'll find that experimental physics is a category of disciplines and subdisciplines in the field of physics, and so on and so on and so on, everything you know about it. I wanted to show you just two early examples of experimental physics. This is a very early telescope. It was found last year in a piece of mud close to where the new station of Delft was being built. In the Netherlands, there is a rule: if you want to build a new building, there is the rule that there should first be archaeological studies. So this is a pedagogical university, right? So it embraces lots of disciplines. That means that you have to go to various areas. Archaeology might be one of them. So this was found, and initially they thought it was from a bullet, right? I mean, you have those bullets which you go when you are shooting deer in the woods. But on closer look, they turned out to have two lenses on both sides. It was a very early telescope from the early 17th century. Remember, Galileo was 1608 when he looked at the moons. And this is one out of the same time. And it's very nice that it's still available while you're building a new station. This was another one of that person that I was referring to, van Leeuwenhoek. He was not interested in looking far ahead where the enemies were. He was not interested in the stars, but he was interested in tiny little elements. So here you see a description of his van Leeuwenhoek microscope. It contains a little mosquito here. There's here a little lens, that's the lens here. And then he could sort of position it with this in order to get it into focus. And this is the one that was found a couple of months ago in a dollhouse in England. So someone wanted to throw away junk, and in that dollhouse, they found a very precious microscope from van Leeuwenhoek, and this one was silver. So there are lots of brass, or lots, 11 or 12, but this one was from silver. And it was a beautiful piece which they planned to throw away. Found a couple of months ago. Very interesting. That's early experimental physics.
Just some names are not recognizable.
Okay.
So his name is Leeuwenhoek.
Well, his Dutch name is van Leeuwenhoek. So there is many names in Dutch, they start with van, and it means that that person came from the Leeuwenhoek. So Leeuwenhoek was then a lion's corner, it is the word, but van goes in front of many of those names. But Leeuwenhoek, that's a name that you recognize. Yeah? Okay, now let's move on to superconductivity and its applications. So this is a cartoon from Nature, which appeared a couple of years ago when it was commemorated that superconductivity was found 100 years ago. And then nobody expects a superconducting ground state. That's what Kameleon says. And then it goes one person after another, and it looks as if superconductivity is everywhere. And that is one of the striking things. It is a completely new phenomenon discovered 100 years ago, and then if you look closer, it turns out to be everywhere. That's very fascinating. And also, there are interesting applications. Now, this is too quick. So I understood that in the audience, I might have first-year students, second-year students, third-year students. Who is a first-year student? Who is that's about 10. Second-year students? Well, that's 20. Third-year students? Only 2. Oh, 3. Okay, so what is the problem? They probably have taken a course on solid-state physics and they think, well, that's too difficult. I run away from it. Okay, at least in our curriculum, in the first year and the second year, you do not get solid-state physics. You only get it in the third year. But let me just go with this little flow diagram from a book that we use. So it starts with crystal structures. And then you have here free electrons, you have here magnetism, you have, again, crystal dynamics. And so sort of here as an isolated piece of material, you have superconductivity, but you have also magnetism here, and you have semiconductors. And this is all a whole zoo of subjects you have to study. Superconductivity is always a little bit at the periphery, because it is very easy to pay tribute to these gentlemen, because in the early 1920s, the core of solid-state physics was created. And if you look at this picture, it was originally black and white, and some company has colored it so that everyone has a suntan. And it's very nice to just look at this distinguished group of people who were at the Solvay conference. This was a company who made soap, and they had money, and on the basis of that, they invited people to come for a prestigious conference. And if you look at this, who's this? This charming fellow. That's Schrödinger, of the Schrödinger equation. Look at this. This is Pauli, of the Pauli principle. This is Heisenberg, of the Heisenberg uncertainty relations. Of course, this person you also know, because he's sort of an icon, but he's sort of a weirdo. But this one you take more serious, because it was a Dutchman, Lorentz. And here there is Kramers. This is Madame Curie. You see, females are underrepresented at that time. And now it's a lot better, you know. And so this is Max Planck. This is van der Waals. Here is Niels Bohr. And this is Max Born. So it's a very interesting, and you also may wonder, which language did they speak?
German.
Perhaps. A Frenchman speaking German?
There is one professor from this physics department, and so they conference.
Who is that? Where is he?
I cannot distinguish.
There's no Russian name on this.
His name is Polsky.
Who?
Polsky.
I don't think.
He was the single person from this conference, and he is not a Nobel Prize winner.
Okay.
All of them are.
Well, not all, but.
So he's famous because he did receive Nobel Prize.
But it's very interesting. It's 1927, so there were also other Solvay conferences. But at that time, you have to realize that everything you learn in a solid-state physics course was created in the early 20s. And that is sort of now our standard vocabulary. And that's why the third-year students are not here now. Okay, but now we have to go back because superconductivity was discovered in 1911. And around 1911, what did people know? People in general do not know a lot, right? We all have to grow. But around 1911, what did they know? So they had a whole series of decades about atomic spectra. So you go to your quantum mechanics textbook and you learn about atomic orbitals. You have a nucleus and you have all these electrons around it. How is the picture actually coming through? Okay. That's embarrassing. There are orbits drawn around it. That doesn't show up here for some strange reason. But you can see this is the periodic system. We all know it comes from Mendeleev. And you can see that each atom has its own typical fingerprint. So you can always go into the lab and measure them, and then you have the spectrum of sodium, which you normally do. And so that was all very well known. It meant that people had an understanding of a nucleus and electron orbits around it. And that you can also buy a nice tie on the basis of that. But if you now move on, you want to raise the question, how do I go from atoms to conduction? Because superconductivity is a special kind of conductivity. So we first have to speak about conductivity. And we all know our friend Ohm, who essentially said, if I take a wire and I run a current through it, there is a relationship between the voltage and the current, and that we call the resistance. And that's a linear relationship. That's what he found in copper and in all kinds of wires. But you have to understand the process of conduction on the basis of those atoms. That's not easy, because you have those atoms, you have the core, and the electrons all belong to the atom. Now, you know that there are valence electrons, they can easily go away, so they can sort of sneakily go through the matter like this snake kind of behavior. or they can go between the letters and then bounce back and forth. And how do you describe that? How do you do that right? And at that time, it was not very clear. And this is then the picture of the prevailing theories at that time. You had a theory of Lord Kelvin that if you take, I should say, the question that we have is electroconduction as a function of temperature. So I can raise the temperature like with a glow bulb, then the resistance gradually goes up. You can easily see that. But if you lower the temperature, then you know that the conduction gradually goes down. That was very well known. But now you go lower and lower in temperature, and then the expectation was that according to Lord Kelvin, it would go up. According to Mr. Martien, it would stay constant. And according to Dewar, it would go down to 0. Now, what were the original ideas of these persons? You did not have quantum mechanics or anything like that. So Lord Kelvin was thinking, okay, these free electrons from the atoms, they freeze to the atoms. So they are no longer kicked out, but they are absorbed by the electron again. So you lose free electrons to move through the material. That's what and we now know that is what happens with semiconductors. With Martien, he was focusing on if you have these electrons going through the atoms, it is scattered. And then he said, well, you have vibrations of the atoms, and gradually you have also impurities. And then if you lose the vibrations, you are coming at a plateau, and then you are left with the electrons which are kicked by the impurities. And that is still how we think currently about it if we ignore superconductivity. And Dewar, you could say, that was a bright fellow, because he was anticipating that the conductivity should become infinite, say the resistance should become 0. Now, that is this prediction, what he had here. What was his idea? He was simply ignoring the impurity resistance of Martien, and he said all these vibrating atoms, they become more quiet, more quiet, more quiet, and then it becomes easier to go through all these atoms. So those were the three, and you can imagine that it therefore is worthwhile to try to go to lower temperatures to understand better the conductivity. Now, just a few more words. If you are now going to those friends of ours from the Solvay conference, and you take the modern understanding of normal conduction, it is always referring to electrons as waves. And if you have waves which go through a periodic lattice, and that matches nicely, then it becomes very easy. Then you are no longer so, I mean, if you take a lot of poles here, and you have a wave coming through it, that goes easily. But if you shoot a soccer ball through them, it becomes very difficult. So as soon as you start thinking about the electrons as waves, you become a lot more happy. But then still, you prefer to have a periodic lattice. So any defect that you might have in your periodic lattice is still painful for your conduction process. And that is in our solid-state physics courses. And if you like to understand a little bit more how a collision goes, then we do this, right? So this is how electrons and phonons are, and electrons and crystal lattices are colliding. The picture does not show up very well. I go quickly further. So, getting back to that conduction, this is now the situation that we had in the early 20th century, so around 1908. This is Kamerlingh Onnes. He was a person, his father was a company owner, and he wanted to be a professor or of some kind, not knowing what that would mean. But he was a great admirer of this person. This is van der Waals. So in Amsterdam, there was a Professor van der Waals, and he has all these theories about liquids and gases and so on. So he explained to Kamerlingh Onnes what would happen if you do refrigeration. And Kamerlingh Onnes was taking his lessons as a guideline for making a cryostat. And this is one of the second generation of his cryostats. So this is a glass dewar, which can be made in a glassblower shop. It's no longer being done, but when I was a PhD student, we still were using those. So this is vacuum here. Then you have one which is filled with liquid air. Then you have one filled with liquid hydrogen. And then you have here liquid helium. And in this case, he had an additional reservoir of liquid helium here, and he could pump on that. And therefore, it reached a temperature of 0.83 Kelvin. And the previous generation that he had was not having this extra one here. So now you have the problem of electrical conduction. And you have the situation that you have been able to cool further. So this is the cryostat to cool. And what are you going to measure if you are in the cold? I mean, it's far away. What can you do? You cannot shine light in it because it was covered with silver. So the only thing you could do is electrical conduction, right? And therefore, he started to measure electrical conduction. And this is his notebook from Leiden, 8th of April, 1911. And now we are struggling again with the... Uh-oh. I'm really sorry about that. If you want to see it later, please come to my screen. And if someone wants to have my slides, I will leave them here. But yeah. So here I've underlined 3 Dutch words, and that's here in red. Kwik, nagenoeg, nul. So I think you understand what null means, right? Kwik sounds like mercury, isn't it? Yeah. Nagenoeg, that's a Dutch word, and it means practically zero. Yeah. So so what you see is here that he is looking at mercury. Why would you take mercury? Well, you know you have mercury thermometers. In the laboratories at that time, mercury was very popular because you could easily use it for expansion, you could easily shape it, and then if you take a glass bulb, you could have a droplet of mercury, which was then highly purified, and you would have 2 contacts on both sides and seal it off with a glassblower's tool, and that was put in the cryostat. And then what you can see here, or not see here, the resistance comes down here, and then you reach a point where it jumps to 0. And this happens at 4.4 Kelvin. So you may wonder, why did he take mercury? The reason was that that was one of the substances which you could easily purify. So how do you make pure materials? That's always difficult. But since this was a liquid, you would see the dirt floating on the surface, and then you could remove it. And you could also apply a distillation technique to get it purer. So that was the reason that he was using that. And he was very lucky that it was superconducting in the range of temperatures that he could measure, because the TC was 4.4 Kelvin, and he could only go down to 4.2 Kelvin, or maybe 2.0 Kelvin, about that. And this is that famous hero. Now, if you now go further, and you take our friend Mendeleev's, well, not his periodic system, because when Mendeleev made it, there were a whole bunch of elements not yet discovered. But currently we have now many more. But what you can see, all these red ones, they are all superconducting. The green ones are superconducting under pressure. And the yellow ones are superconducting in a modified form. So this whole periodic system is quite full of materials that are superconducting. And here you see a picture. I mean, these were the predictions, right? And you see that this gradual going to zero was not what you got. You got something that jumps to zero. And that is with thallium, mercury, with tin, with lead. Cadmium, you could not see it, but they didn't go low enough. Cadmium is also superconducting, but they didn't go low enough. So it has now been observed in numerous materials. And then the next question is, how do you solve it? I mean, how do you crack that nut from 1911? That's very difficult. You need many bright people. Part of it, this slide is Nobel Prizes in physics related to superconductivity and superfluidity. In this case, it is added superfluidity because later it was found that liquid helium can also show something analogous to superconductivity, namely superfluidity, and that means flow without any resistance. And therefore they grouped that together. And it's 17 persons in total were needed to actually crack that nut. It starts with Kamerlingh Onnes, and then a very early contribution was from Landau, and that went, and that was on the subject of superfluidity. And then these three persons are the real big heroes of superconductivity. This is John Martien, this is Leon Cooper, and this is Bob Schiefer. This is the only Nobel Prize winner in physics who has won 2 Nobel Prizes. When he got the Nobel Prize for the transistor, he felt it was a nuisance, annoying, because he was just busy in making the theory of superconductivity. So then you cannot have a Nobel Prize knocking on your door. And then in 1973, you had Brian Josephson and Kiever contributing to the superconductivity of tunneling. And then you had also Kapitsa, who also did a lot of work on superfluidity. Then we go down on the row. Those are 2 more recent ones, Bednorz and Müller, who discovered a new superconductor with a very high critical temperature. And then here we have 3 persons who have contributed a lot to superfluidity. And then Laughlin is in this list also, although it is the fractional quantum Hall effect, which is also some kind of superfluid. And then we have here Abrikosov, Ginsburg, and Tony Leggett. So again, a whole a panorama of very bright minds who all contributed to this field. And since we are now here, you could say, okay, why should I mention that here at Moscow State Pedagogical University? Well, because if you go to the graveyard next door, which you can always do over lunch, you can always find some of our respected heroes. So this is Kapitsa's grave, this is Ginsburg's grave, which is there now, and this is Landau's grave. So it's very nice to see that. Well, there's one danger. I mean, I'm not sure which one of you will get the Nobel Prize. Who has the ambition to get the Nobel Prize? Okay, here we have one. Good luck. But no, that's a good ambition. I think my days have passed on that. But now we have to move on. So this is a quote that I took while I was preparing this talk. And it's from a story written by Sébastien Balibar, a French experimentalist theorist about superfluid helium. And he has been studying the history of superfluidity. And that's very interesting because Landau's paper on that was written in 1942. You remember something happened around that time? I mean, we have had some people speak about the war, right? And then you have all the Jewish people who were under pressure. So it's a very complicated time. Landau published it in Physical Review in the United States. Very interesting at that time. But if you look at the whole story, he then looks into the details of who has been contributing. And he says, well, if we focus on all those heroes who want to get the Nobel Prize, we also have to pay attention to look at the people who did not win. So he goes painstakingly, carefully, as a historian, to find out not who has not won, but who was making very significant contribution to that field. That's highly recommended because of the turbulence of the time, and at the same time, the difficulty of identifying who deserves the glory. Now I go to, well, how am I doing on the time? When do I have to stop, Mr. Chairman?
Nothing special.
Let me at least, who wants to see his girlfriend or book? Or
Boyfriend.
Boyfriend, yeah. So I'll pay attention to the time myself. So now we come to the superconductivity. We have seen that it comes down and then it goes to zero at a very sharp point. There's no doubt about that. There's very peculiar something happening. And it took until 1957 to make the theory. This theory is made by Bardeen, Cooper, and Schriever. It's now the celebrated BCS theory. One important ingredient is summarized on this slide. It's, again, going back 2 electrons and a lattice. So it's again that crystal, you have the atoms, you have the electrons. Now, if take 2 electrons, have them in mind. One of them is moving in that direction. This electron is negatively charged, and the atoms are positively charged. So what you see is that these atoms are pulled towards this electron, which is zapping by. But this is then going out of sight. But there's another electron which is coming in, like here. And then this electron now finds that there is an excess positive charge there. So this electron experiences that as that he is pulled towards it. So whereas this electron deformed the lattice, this electron is experiencing that deformed lattice. So that means that there is an electron-electron interaction mediated by the deformed lattice. Now that's called electron-phonon interaction. So phonon-mediated attraction between electrons. If you go further, after 1957, there are all kinds of other proposals of possible attractive interaction. But this was the one that BCS introduced. And then they went, and they were suggested to do that.
What BCS stands for?
Bardeen, Cooper, and Schriever. The 3 persons that I had in the center of my Nobel Prize list. And Bardeen was the one who had also the transistor invention. Okay, in this picture, which also is not very clearly shown, is the critical temperature at which the material becomes superconducting is listed for different mercury isotopes. So you have then a crystal of mercury with different different weight of the nuclei of the mercury. So those are heavier. And the TC is dependent on the weight of those atoms. And that suggested that the phonons and the lattice should play a role. Now, so this is one thing of BCS, electron-phonon interaction. The second, an attractive interaction. So 2 electrons are pulled to each other. There's one other thing which is important at that same time, and that's called Kiever tunneling, another of these Nobel Prize winners. This is Mr. Kiever. He is from Norway originally, but he emigrated to the United States as a mechanical engineer. And then he felt that he did not have enough schooling, and one of the things that he needed to learn more is physics. And one of the things that he could not understand is quantum mechanics. Well, imagine a mechanical engineer understanding quantum mechanics. That's sort of hopeless. So he was struggling with a picture like this. I mean, some of you might come across, or soon will come across, say, calculate the transmission of a rectangular potential well, or, right? So you have to have a wave coming in, and then there is a finite probability to go through, and you do your mathematics and so on. But, or his name, Kiever said, I don't understand that. Can't I measure that? And so what he did, he went to the laboratory and said, well, okay, I take a simple bell jar, which I can use to create mirrors. So just aluminum deposited on a glass plate so that you have a nice mirror. And then, so he took such a glass plate and he made a stripe of aluminum. Then he exposed it to the air, and then aluminum oxidizes. And then he put on top of it, in a cross, say in a cross configuration, another electrode of lead, which was also easily deposited in this system. And then he started to measure, say he would have the current going into one of the leads and then taking it out in one of the others. So in essence, he was saying, I have electrons coming in here, and I have an oxide in between, and I'm looking how many electrons come on the other side. What do I find? Well, he found a linear line like this. So I and V, just linear, originally. And then he thought, okay, I have a leak. It's just Ohm's law. It's sort of the same 100 years old Ohm, which is giving my results. But then someone suggested that he should cool it down. He should go to the cryostat, which was available there, and to see what happens. And then he got this nice curve. Now, what does it mean? Originally, you had this. Here, you have a normal metal, which is filled with electrons to what's called the Fermi energy. You can also have that on the other side. If you study that, it's very simple. There is a probability of electrons going to the other side. Here are occupied states. Here are non-occupied states. And you have just a linear line. But if you now go to the superconducting state, there is something which BCS had predicted, and it is much too technical to go into details now on that, but you have an energy gap. And the reason is, if you have electrons attracting each other, and you go to a state where all these electrons become a pair, then there is binding energy between them. So in order to get free electrons, you have to break those pairs. Now that breaking of the pairs is this energy gap. So you have to have at least 2 delta of energy to break the Cooper pairs into free electrons. So that means that there is a gap in the spectrum where no states are allowed. And that means that if you now have here a normal metal here, and you have here a superconductor, all the states in this energy range are blocked. And that's what you see here. So you increase the voltage, but only if the voltage goes above this point, the electrons can flow. And that's what you see happening here. And if you could cool this down to real very low temperatures, you would never find any current down here. So this was a discovery by this poor mechanical engineer because he wanted to understand quantum mechanics, but he was measuring then something which is very deep predicted by the BCS theory. And nowadays, we are routinely making those same kind of tunnel junctions, as they are called now, as Kiever first introduced. And they have become completely connected with the nano world. Okay, so what have I done so far? I have sort of gradually brought you into hopefully the essential concepts of superconductivity and how it comes about and so on, and also the peculiarity. And you need a whole course to start to understand everything, and you can also continue to work on it for your whole life. at least that I've done that. But let me take 2 examples where you can come across it. So if you have something like you hurt your knee or something like that, you go and get an MRI. So that's one application that's medical. And there is another one which I've been closely involved with, that you measure the presence and type of complex molecules in the universe. So you look into the universe and you look whether there is carbon monoxide or whatever. And so it's very important for astronomy. But I could make this list much longer, but that's not what I want to do. So magnetic resonance imaging, it really starts with something very elementary. If you have a material which has a zero resistance, well, the first thing that you think is, well, we could make a magnet out of it. We would take a wire and we make a coil and we run a big current through it. And if that current can be big enough, I can get a huge magnetic field. That has been done, but at the same time, it's a specific subfield of engineering. You have to develop cables which are suitable, because if something along that cable happens that, for example, there is a fluctuation and that it is therefore temporarily normal, you get dissipation, and then all of a sudden it heats up. And that's what you want to avoid. And therefore, what people have done is you have a mixture of superconducting material and copper. So these are copper, and this is horrible. I mean, you cannot see this, but this is from a company in Japan who's making those superconductors. I will read what even I cannot read it now. Okay, so it goes up to currents of 1,000 amperes, and it gets up to fields of 19 Tesla. And so that's a real, very high field. And for example, this is an MRI system with the highest field that is available, 12 Tesla. You see a person in here. This is a big superconducting magnet. Here is the liquid helium. And then you have extra coils here. And now the question is, how do they actually work? Why do you get your MRI image? That works as follows. You have to think about your body as having, again, atoms. These atoms can be tiny magnets which are precessing in a big magnetic field. Now, so this is an example of an atom, a proton, and there's lots of protons in your body, and they are doing like this in that high magnetic field. Now what you can do, you can have now an extra magnetic field which flips this precessing atom in that direction. And then you start looking how long it takes until it goes back to its original position. And this process, how long it takes, provides you information about the local condition of the fluid. Yeah? And so it's using atomic magnetism. So this is a picture. So you can have here all these little atoms running in all kinds of directions. Then you apply your big magnetic field, and they all line up then. And then you have your pulse in that direction, and then you see them all line up in this direction, and then they go back through the mutual interaction to the original position. And if you do that right, you get this. So this is a snapshot through your brain, or at least someone's brain. So you make slices of the brain. You start here, and you go. So you start here, and then you go more and more and more and more and more to the side, and you see you can follow it. And here you see only the ear. Yeah. My daughter is a neurologist, and she uses those pictures all the time. And then she doesn't know anything about superconductivity. And I try to tell her about it, but she doesn't get excited. So this is the closest to home application of superconductivity. So it's really something that is at all the hospitals available. And pay attention, it's liquid helium, superconducting wires, and it's a very complicated signal processing thing, but then you get beautiful images. Now, there is one other mechanism, one other application. I already referred to astronomy. That again goes back on that same person, Kiever. That is the detection of electromagnetic waves. This is the picture that I had before. So you have a normal metal here and a superconductor here. Now, this is the same sort of plot, except that the voltage is in the vertical direction and the current in this direction. Now, if you shine radiation on it, you get all these tiny little steps. That was discovered in 1962. And then people put it aside. There came a paper from a person named Josephson. And Josephson that paper was so glorious, only 2 pages long, that everyone who wanted to use superconductivity started to use the Josephson effect. That was a very, very big mistake. It was useful for some, but in this particular case, they should have stayed to this. The Josephson effect is that you have here also a supercurrent. That means that through an insulator, not only a normal current flows, but also a supercurrent. And that's beautiful, but useless. Now, not quite useless, but anyhow, for this it was useless. Okay, now, if you are in astronomy, suppose you are fascinated by that. You have heard about the cosmic microwave background. Yeah, so that from all directions in the universe, you get then the information, and it can be described with the radiation curve of Planck. Well, normally, when they teach you that, they say you have a peak at 7,000 Kelvin here, for 6,000 Kelvin here, for 5,000 Kelvin here, for 4,000 Kelvin here. So it shifts from blue to red. Now, from the universe, it's also the same black body radiation, but from a temperature which is 2.7 Kelvin. Which frequency is 2.7 Kelvin? If you go to the description of the Planck's curve, you find that it is 160 gigahertz. So if you would like to see in the universe the furthest away parts, you have to be around frequencies like 160 or 200 gigahertz. So you need to be able to detect that. And that is a challenge. Well, to do that, what happened was that the European Space Agency has launched on 14th of May 2009 a rocket, an Ariane rocket, with 2 instruments on board, or 2 satellites on board, the Herschel Space Telescope and the so-called Planck satellite. This one is the one that both Gregory Koltzman and I have been contributing, each in his own way. The Planck satellite we have not been contributing to. Both of them are cryogenic satellites. So they are cooled with liquid helium. And they only run as long as the liquid helium is available in that big bell jar in the universe. So then it's launched from French Guiana, and then it goes into the so-called L2 orbit, and this is the orbit for Planck, and this is the orbit for the Herschel telescope. And in April 2015, so last month, these pictures have been released from the Planck satellite. This is for 30 gigahertz, 70 gigahertz, and 353 gigahertz. And you need to imagine that it's looking at fluctuations in the temperature on the level of microkelvins. So you have 2.7 Kelvin, and then plus or minus a few microkelvins. That's the sensitivity, and that's what they have done at different frequencies. So it's quite impressive. But the other satellite, that is the Herschel space satellite, and that has 3 instruments on board, and one of them is the heterodyne instrument for the far infrared. That is equipped with superconducting devices. And that has been measuring the astronomy. So you know you have to do a lot of technology then. And then you get this. So this is 1 terahertz, about here in the middle, and then 100 gigahertz in both directions. And this is the color is the background, but what you see here is all these spectral lines. So you need to identify all these spectral lines to find out what there is out in the universe. And what you find is methanol, methyl format, deuterium cyanide. But most importantly, you find water. So imagine that it was not possible to measure from the Earth whether there is water elsewhere in the universe. You can get wet here on Earth, but you cannot see what's happening there in the universe. So since you are with the satellite outside the atmosphere, you can easily see it. So now it's known how much water there is everywhere in the universe, and that's very important. Okay, so those are the 2 applications that I wanted to show. I have 2 or 3 more slides. The first thing that people always ask, can't you find a superconductor which is superconducting at room temperature? People have worked on that very aggressively. This is a plot of how the critical temperature has evolved over the number of years. So it started out a long time ago, then it goes up gradually, then it jumps and it jumps. So it has gone all the way up to 170 Kelvin. But these materials have become more and more complicated. But most important, this is so, I have to do something about my own slides, I guess, at least, or the projector. But here, this is a description of these new materials, and people are now equally puzzled about what is causing that superconductivity in these new materials. Say, from 1911 to 1957, it took a long time to get a BCS theory. It is still to be answered, so that's where the Nobel Prize is, to find the theory of these new materials. And then, so the Laboratory of Quantum Detectors, which is in this building, it centers around nanotechnology. You have to make small things. It centers around superconductivity and interaction with photons. And here you see a picture of one of my former PhD students who is then repairing something of the Herschel Space Telescope. So that's Peter Dieleman. We had a conference here in Moscow, and this is a whole range of 5 of my PhD students on the Moscow River in the site of the Kremlin. This is one of the PhD students, Nathan Verkruijsen, together with Boris Voronov, who is running the clean room here. And this is then our cryostat, like Kamerlingh on his head, going down to lower temperatures. And this is now operational, and you can see people still not looking really enthusiastic, but they had problems to solve.
Yeah, what are the tag for the highest superconductivity temperature today?
Well, that was on the slide which it was 180 Kelvin. So
180,
yeah, so that's well above liquid nitrogen temperature. Yeah.
Please tell us a few words about cooperation with laboratory of our Professor Wolfsburg and our methods compare with your methods.
Well, first of all, I am retired at Delft, so I had a little bit more free time, so I can just play. But I would say, first of all, I think one of the things that we have in common is that it is a laboratory at a university. So I have been a great admirer of genuine research universities, where you have young people who are eager to learn something and embed it in research. And it's fine that people come in and work 4 years as a PhD student and then move on to other jobs. At least that's in the Netherlands the case. So I think 60% of my PhD students have not found a job in physics research. Not that they have desperately trying to get it, they were happy to have that education of 4 years, participating in international research, writing scientific papers, and then subsequently going into the banking or into a commercial enterprise or whatever. That is a very common method. So that's a very important point, but it means that you then can combine sort of development of young people with research, because I am then an educator and a researcher, and I work with young people, and some of them want to continue, but others move on. But we both have had fun. And that is something which is characteristic of our university, and which is also the case of Moscow State Pedagogical University, except for the fact that it is always the emphasis on the P, so that it is pedagogical, and I never know precisely. I would never like to have a university only zooming into educating teachers. I think specialization university is always a little bit complicated. Or I would say it's not the best way forward, let me put it this way. Let's not judge the past. And then on the concrete level, Professor Coltman's laboratory has done a lot of work on superconducting films and photons. And my attitude has always been, I don't want to be an engineer who makes things and then moves on to the next thing to make or develop. I want to understand it. I want to be a person who is what you call a practical person who also thinks about what he is doing. And that's the way I'm also interacting now with the people here. And I think they enjoy it. What do you think, Ivan? Okay. Don't say no, otherwise I'm wasting my time.
Sure.
Let me ask you one more question, perhaps if nobody else, that will be the final one. Can you very roughly, in a few words, explain something about the results of your joint research here in Moscow?
Okay. Yeah, where should I start? So what can I take as the best example? Say? Yes, I could take diamond.
Diamond, yeah.
Why not diamond? So I'm a specialist who has been working on non-equilibrium superconductivity, like the person you referred to, Eliasberg. That means that you say, I take a superconductor and I shine radiation on it, bring the electrons to a higher state, and I look how they relax. A little bit like what I said over the MRI. And so, and I know that in the tradition of the lab here, that has been done with materials like niobium nitride. And then I was at a conference, and I learned about people who had diamond films, which were superconducting. And I thought, it's funny. And then I was starting on the airplane to hear, and I thought, well, if we now ask the French to provide such a sample, and that could then be measured with the equipment here, we must be able to write a nice paper, and that's what we are currently doing with Anna Karakova. So the results were very nice. It is a new material, and it's very new because normally you have a superconductor on a glass plate, and then you never know how the interaction of the superconductor with the glass plate goes. In this case, you have a diamond crystal, and on top of it, a diamond film is grown by the French, and they put dopants in it, like boron, like in a semiconductor, and therefore it becomes superconducting. So it's sort of diamond all the way, but then with extra dopants in it, and because of that, it's superconducting. It's a very unique system.
Yeah, it's naturally for a Dutch person to use diamonds.
That's Belgium. The Dutch do. But this is an example of how I collaborate, also contributing to ideas, and that means that's one of the funny things, that this is a conference that I attended in France, and I had seen that person before, but because I was here, I made the click with the equipment here. And then it takes a little bit of time to get it arranged, but it works out.
Thank you.
One more question, I guess. First-year student with a question.
Yeah, to introduce myself, I'm actually from Sweden. I'm originally from Germany, but I work in Sweden at Teunis. And we really recently started also a cooperation with Professor Golfman now. And I started measuring my niobium nitride films, and we were after vexation time. So it goes really international, and I'm very glad about this cooperation that we started here recently. And I also had a very fruitful conversation with Professor Klapwijk yesterday. And I have a couple of more questions later on because they're pretty much in detail. So
I'm flying back tomorrow. But now what I will do is I will make sure that my talk is present. It will be left here so that you can read the slides. I'm sorry about that, the quality. I need to...
It's a problem of resolution of the projector, of the beamer, and your original screen, because screens are better now than beamers, and so that's why it doesn't fit exactly.
So you're the rector, right?
Yeah, I shall.
So that's...
I was thinking about this, how much is the price tag? I estimate it perhaps as kind of 4,000 euros.
So there's one other topic that I could mention. So I also know the great tradition in the theoretical physics in Russia. So I'm also working with Sasha Semenov here, together with Igor Deviatov from Moscow State University. And we are working together to explain certain experiments that we have done in Delft. And one of the things that I would love to see getting stronger, I mean, everyone knows the history of your own country. So at least I understand, and if not, then try to read books about that. But so when I was a PhD student, all these names were for me, I had to study the Keenesburg-Landau theory. I was learning about the Eliasberg effect, and I was doing experiments which were explained by that. I've been working with Artemenko, Volkov, and Zaitsev. I have a paper which has been cited many times with Volkov and Zaitsev, who are from the Institute of Radio Engineering. So it's a very great tradition, and the reason that I felt sympathy to come to Russia when Gregory Koltzman proposed me that as part of my retirement and pointing out the opportunities, I really felt that it was a means to pay certain things back. At the same time, I also see how enormously difficult it is to build up that great tradition, and the great tradition was part of the political conditions at that time, which is sort of sad to say, because you do not want to create a political situation of that time back again in order to create that science. So it's a very important challenge that Russia faces to improve the science again, and one of the temptations is, in my view, continuously that you have to focus on the content and not on the critical performance indicators. I come so often across certain things that I have to do in the context of the mega grant that I think, yes, but that's not what it is about. It is just then filling out forms and so on. And that is a disease which I only can encourage. Do not fall victim yourself to that disease, but try to push that aside as much as you can and focus on real interaction between research, education, and international collaboration.